Welcome back, design junkies, to Mechanical Engineering Made Simple.
Today, we are moving flat. We've talked about linear beams and vertical columns, but now we're diving into the world of flat plates.
Right. And this stuff provides the fundamental mathematical skeleton you need to predict stress and deflection in things that are, wide and thin.
Exactly. Things like floor slabs, pressure vessel caps, or even something as small as a circuit board.
That sounds deceptively simple, though. I mean, a plate is just a flat piece of material, right? But the math gets complicated really fast because the stress isn't just running along one axis.
It's biaxial. And our mission today is really to pull out the core insights, the formulas, sure, but more importantly, the conditions that tell you when you can even use those formulas.
It's a fine print.
The fine print. Because these foundational formulas for flat plates, they are not universal truths. They rely on very specific linear assumptions. And if you break those rules, the math it falls apart instantly.
So why do we always start with these assumptions? If, real-world plates are never perfectly flat or uniform, how much error are we baking in right from the start?
It's all about setting a reliable baseline. We start with these ideal conditions. We can call them the sacred four assumptions to make sure the math is actually solvable with linear elasticity.
Okay, so what's rule number one?
Rule one is that baseline. The plate is perfectly flat, it has a uniform thickness, and it's made of a homogeneous isotropic material, meaning it acts the same in every direction.
Simple enough for a textbook, but in the real world, materials have flaws.
And that's why we have safety factors. But the next two assumptions are structural constraints you really can't ignore. Number two, the plate has to be relatively slender.
What does slender mean in this context?
Its thickness, let's call it T, can't be more than about 1/4 of its smallest width or length. If it gets too chunky, shear effects start to take over, and this simple bending theory is, well, it's just wrong.
Slenderness is key. And the third one, that has to do with movement.
Yes. Maximum deflection has to be small. And crucially, that deflection should be no more than about half the plate's thickness.
Half the thickness.
If it starts to sag too much, if the deflection is greater than T divided by 2, you get these nonlinear effects, and you have to switch to a whole different method of analysis.
That half-thickness rule seems like a critical dividing line we need to keep in our heads.
It is. And the fourth is the classic disclaimer for all this stuff. Stresses have to stay within the elastic limit. We're talking about deformation that bounces back. If the material yields, all bets are off for these simple formulas.
Got it. Now, let's think about how a plate actually carries a load. When it deflects, where does all that stress actually go?
Well, when a plate bends, you can imagine the material on the top surface is being stretched, that's tension, and the bottom is compressed. But there's a plane right in the middle surface, which remains entirely unstressed.
The neutral axis of the plate.
Exactly. It's a fundamental concept.
So the stress isn't uniform through the thickness at all. It's zero in the very middle and then highest on the outside.
Correct. The stresses are biaxial acting in two directions on the plane of the plate, and their intensity increases linearly as you move away from that neutral middle surface. This means your maximum stresses are always at the outer surfaces.
Which is, of course, where it's most likely to fail.
Precisely.
Okay, let's move into the messy world of real-life loading. One huge challenge is dealing with concentrated or point loads. I mean, mathematically, if you apply a force to an area that's almost zero, you get, what? An infinite stress.
You do. The math gives you an impossible infinite stress value, which we know can't happen. And this is where practical engineering steps in with a really clever fix.
The equivalent radius.
The equivalent radius. It's a way to sort of smooth out that impossible stress singularity.
Okay, so without just reciting the formula, what's the concept? How does this solve the problem?
It basically replaces the actual tiny loaded radius, let's call it r sub o, with an artificial slightly larger value. Let's call that 1 r sub 0. This larger value is mathematically derived to give you a finite, realistic maximum stress.
So the correction factor depends on the plate thickness, T.
Heavily.
So if I have a really concentrated load, the math pretends it's spread over a slightly wider circle, and the size of that circle depends on how thick the plate is. It just keeps the calculation in the real world.
You've got it. If your actual load area, your r sub o, is very small, and the rule of thumb is less than about half the thickness, then you use this larger equivalent radius. If the load is already spread out over a bigger area, you just use the actual value.
It turns a theoretical impossibility into something you can actually calculate.
Yep.
Now, speaking of theory versus reality, we have to talk about edge conditions. Free, guided, simply supported, or fixed. We all love that fixed condition in our models because it gives you maximum stiffness.
And this is where the source material gives a huge, huge word of caution. The theory assumes perfect rigidity at a fixed edge. But the text is explicit. No exact edge condition is likely to be realized in ordinary construction. And true edge fixity is especially hard to achieve.
Just think about welding or bolting something. There's always going to be some tiny rotation, some yield.
And the consequences of that are massive. Even a slight amount of yielding at what you thought was a fixed edge, it greatly relieves the intense bending stresses right there at the edge.
So that stress doesn't just disappear, it has to go somewhere else.
It gets redistributed inward.
Correct.
That relieved edge stress is transferred, and you get this crucial trade-off, an increase in deflection and much higher stresses at the center of the plate.
So if I design for, say, 15,000 psi at the fixed edge, but the weld isn't perfect, I might be dangerously under-designing the center of the plate.
That is the critical risk. And the pragmatic advice for engineers is clear. When you're designing a nominally fixed edge plate, you should probably design for somewhat higher center stresses than the pure theory suggests.
Build in a safety factor for the center.
Exactly. Just to accommodate that inevitable real-world yield at the boundaries.
All right, let's pivot to circular plates. They're everywhere, but analyzing them requires this specialized, almost intimidating mathematical toolkit. It's full of constants and functions.
It looks formidable, absolutely. But the reason for the complexity isn't to punish anyone. It's to generalize the solution. These equations use a system of interchangeable coefficients, like numerical placeholders, to cover a massive number of combinations.
Annular plates, solid plates.
Right. Different kinds of loading, different boundary conditions.
So instead of a unique, complex equation for every single scenario, they made one master equation that's modular. You just swap out the coefficient values from a table depending on your specific case. It's like a lookup architecture.
Precisely. It allows decades of complex analysis to be boiled down into a compact set of tables. And this system lets you get creative. If you have a complex load that doesn't fit a standard case, you could often approximate it by fitting a simpler curve to it.
And then?
Then you break the problem into smaller pieces, solve each one using the standard cases from the table, and then add the results up using superposition.
Classic engineering problem solving.
It is.
I also find the specialized cases fascinating. The ones that are about forcing a lack of flatness from the outside.
Oh yeah, those are vital for modeling assembly forces. For example, some cases handle a manufactured change in slope, which is what you need if you know a specific boundary rotation is being applied.
So it's not about a load, it's about a forced deformation.
Exactly. Or another case deals with a small manufactured step that's forced to fit a boundary condition, and it tells you the reactions needed to make that happen.
Let's try to ground all this theory in a practical example. Let's take a solid circular steel plate. It's simply supported along its edge, and it's got a uniform load, maybe from fluid pressure.
A classic scenario. So let's say we have a steel plate that's 20 inches in diameter. So that's a 10-inch radius. It's pretty thin, only a fifth of an inch thick. And it has a uniform load of 3 pounds per square inch.
Okay, we know the properties for steel high, modulus of elasticity, E, and a given Poisson's ratio. What do the formulas spit out?
Well, the first thing we calculate is the plate constant, D, which is all about the stiffness of the plate's geometry and material. Once you have D, you can find the deflection. For this case, the center deflection comes out to be about negative 0.083 inches.
So under that pressure, the 20-inch plate sags by less than a tenth of an inch. That's a pretty small displacement.
It is, which is good. It confirms we're operating well within that small deflection assumption we talked about.
Okay, what about the stress?
The formulas give you a maximum moment, Mmax, and from that we find the maximum stress at the outer surface, sigma max, is 9,240 pounds per square inch.
9,240 psi. So for a common steel, the yield strength might be, what, 36,000 psi or even higher?
Exactly. So the point is that this calculated stress is quite low compared to what the material can handle. The numbers prove the design has a large safety margin built right in. All those complex functions just collapse back into a clean, predictable set of numbers.
And that's why we trust the tables.
Moving beyond just basic bending, we should probably talk about something that's often ignored in thin plates: shear deflection.
Right. You mentioned earlier that shear is usually ignored because its contribution is tiny compared to the deflection from bending.
It is for thin plates. But for thicker plates, especially annular plates, the ones with big holes in the middle shear can become a pretty noteworthy percentage of the total displacement. We need a clear threshold for when to worry about it.
And what is that tipping point?
If the thickness, chi, is greater than 1/3 of the difference between the inner and outer diameters for a simply supported plate, you have to include shear deflection.
And if the edges are fixed, that threshold gets even smaller, doesn't it?
Significantly smaller.
Yeah.
If the edges are fixed, you have to include shear deflection if T is greater than just 1/6 of that difference.
Which makes sense, because the edge fixity is already restricting the bending, so the shear part of the deflection becomes a larger piece of the pie.
That's a great way to put it. It becomes non-negligible much sooner.
Okay, let's turn to some specialized materials. What about bimetallic plates? You laminate two different materials together, and you've instantly got a non-uniform problem.
A sandwich plate. Yeah, it introduces complexity right away. If the Poisson's ratios of the two materials are really different, the plate develops this internal in-plane strain that just complicates everything.
So how do you handle that? How do you simplify it?
To manage it, we calculate an equivalent plate stiffness and an equivalent Poisson's ratio. It's a method that lets you treat the layered plate as if it were a single homogeneous plate with slightly tweaked properties.
It's a mathematical compromise to keep the design practical.
It is. But here's the really crucial insight about bimetallic plates, and it has to do with heat. If you take a standard single material plate and you heat it up uniformly, it just expands, stress-free.
As long as the edges aren't restrained, yeah, it just gets bigger.
But a bimetallic plate, because the two materials have different coefficients of thermal expansion, a uniform temperature change will cause flexural stresses, even with no external restraints at all.
The material mismatch forces it to try and curve.
Exactly. Temperature change itself becomes a form of self-loading. You have to design for those thermal curves.
That's a fundamental shift in how you have to think about the design.
Completely.
Let's go back to that boundary condition we started with. The linear theory fails when deflection gets bigger than about half the thickness. When we break that rule, what is actually happening inside the plate?
We shift into the domain of nonlinear behavior. In thin plates, when deflection goes past that half-T threshold, the plate's middle surface starts to get strained. It's not neutral anymore, it's stretching.
So it activates a new load-carrying mechanism.
It does. It's called diaphragm stress, or direct stress.
So the plate stops acting just like a stiff bending member and starts acting more like a drum head or a trampoline that's stretched in tension.
That is the perfect analogy. It begins to carry the load partly through membrane tension, and the result is the plate becomes significantly stiffer than the simple linear theory would have predicted.
And the important engineering takeaway is that for a given load, the stresses will actually be less than what the simple linear theory suggests.
Yes, the linear math is conservative at large deflections. To solve these problems accurately, you have to use these complex, empirical, nonlinear formulas. They have separate coefficients for the bending stress and for that new diaphragm stress.
You have to account for both mechanisms separately.
You do, for any kind of real accuracy.
Okay, let's look at the absolute end of the line. Ultimate strength and plate collapse. This is past recoverable deformation.
Right. For brittle materials, failure is sudden. It happens when the maximum tensile stress hits the material's ultimate strength. Snap.
But for ductile materials like steel, it's different.
For ductile materials, failure is defined by excessive plastic deflection. It's the point where the structure just collapses.
And there's a pretty clean formula for predicting that ultimate load for a common case, isn't there?
There is. For a circular plate with a uniform load and simply supported edges, the ultimate load, W sub U, depends only on the material's yield strength, sigma, and the plate's thickness squared. It's a clean equation that defines the catastrophic limit.
It bypasses all the complexities of elasticity.
Entirely. It's just about the material's yield point and how thick it is.
This has been a really necessary deep dive into the fundamentals of flat plates. I mean, we covered the foundational constraints, small deflection, uniform material, and the practical need for things like the equivalent radius for point loads.
And we highlighted some huge real-world challenges, like the fact that true edge fixity is almost impossible, which forces engineers to design for higher central stresses. And we kept coming back to that critical dividing line. The moment deflection exceeds half the thickness.
That's when you have to switch from simple linear bending to that more complex nonlinear tension membrane analysis.
Right.
So the key takeaway for any design junkie listening is really just to understand your boundaries. Know the assumptions, know when your plate stops being a simple bending member and starts being a diaphragm, and know when to switch from simple formulas to the big tables.
And it's that precise understanding of all these complex stress distributions, the bending, the shear, the tension, that allows for true structural optimization.
For sure. The analysis shows, for example, that you can strategically place stiffening ribs along a diameter of a clamped circular plate, and you can calculate it to achieve the minimum possible weight for a given maximum stress.
If you can calculate every force, every moment, and every potential failure point, from the elastic limit all the way to the ultimate collapse load, you can strip away every single unnecessary ounce of material while still guaranteeing performance.
And that's the ultimate goal, isn't it?
Yeah.
Maximum performance with minimum material.
That's what smart design is all about.
Performance meets efficiency. Join us next time for another deep dive into the core concepts of mechanical engineering.